We are going to continue talking about some different methods for solving the traveling salesman problem, or TSP problems. In the previous video, we talked about the brute force method and the nearest neighbor algorithm. So our question is, are there any algorithms that are both optimal, meaning they give you the best result, and efficient, meaning they don't take too much time, particularly as we increase the number of vertices? Well, the short answer is no. There are no methods that always give us the right solution or the best solution, while also not getting crazy as we increase the number of vertices. So we have a few more methods that give us a little bit better answer, and they are called approximate algorithms. So they give us a reasonably good solution most of the time and are not super inefficient. So they're kind of medium on the optimal scale and medium on the efficiency scale. So let's look at these methods. First, we have the repetitive nearest neighbor algorithm. We talked about the nearest neighbor algorithm in the previous video. So you are going to perform the nearest neighbor algorithm with each vertex being used as the starting point. So you do the nearest neighbor algorithm starting from A, starting from B, starting from C, etc. Then you choose the best, in this case the cheapest, of those nearest neighbor circuits. And then if you need to rearrange it, you can adjust it so that you have the correct starting vertex. So let's take a look at Willy the traveling salesman. So in the previous video, we went through how to do the nearest neighbor algorithm. I'm going to go through how to do the nearest neighbor algorithm again from A as our starting point. So if we start at A, which is where we were told Willy had to start, we want to choose which city is the cheapest to get to. B would be 185, C would be 119, D would be 152, E would be 133. Well, C is the cheapest, so we'll go there. From C, we could go to B, which is 121, D, which would be 174, or E, which would be 120. E is the cheapest, so we'll take that route. From E, we can either go to B for $200 or D for $199. So we're going to go to D. Then from D, we have to go to B, which costs $150, and then back to A, which is $185. Okay, this is exactly what we did in the previous video when we went through the nearest neighbor algorithm. So we had 119, 120, 199, 150, 185 for a total of 773. So then you redo this procedure. So we choose B as our starting point, do the nearest neighbor algorithm. Then choose C as our starting point, do the nearest neighbor algorithm, and continue. So here I have listed out the 5 nearest neighbor algorithms, starting from A, B, C, D, and E. We want to pick the cheapest of these 5 circuits, which you can see that starting from B, C, and D are all the same price. They are all $722. Well, why are they all the same price? Because they're technically the same circuit. All right, I'm going to erase what I drew on this diagram real quick. So if I look at this algorithm, starting from B, I go from B to C, C to A to E, E to D, D to B, And now I'm done. Well, if I look at C, nearest neighbor circuit starting at C, I go C, A, E, D, B, C. Well, that's the same circuit that we have. And starting at D, D, B, C, A, E, D. That's actually the mirror image of the one that we had, but it's all the same circuit. So we can rewrite this to start at A because that's where Willy lives. He has to start at A. So we can go this direction, A, E, D, B, C, A, and that circuit will cost $722. So that is the repetitive nearest neighbor algorithm. The other algorithm we can look at is the cheapest link algorithm. We want to pick the cheapest link, so the edge with the smallest weight available, and mark it. Then we continue picking and marking the cheapest unmarked link that does not either close a circuit or create 3 edges coming out of a single vertex. And then finally, we connect the last 2 vertices to close the circuit. So let's go back here. So we want to look at this graph and pick the cheapest link. So I have ranked all of these edges from smallest to largest weight. So the cheapest is $119, and that goes from A to E. So we can go ahead and mark it. The next cheapest is $120, that goes from E to C. Okay, so we can mark that. The next one is $121. I can't mark that one because if I do, then I have 3 edges coming from C, which does not make a circuit. So I'm going to actually skip this one. Then my next cheapest is $131. Well, that would close off my circuit, so I cannot use that one. The next cheapest is $150 here from B to D, so that one's good. The next cheapest is from A to D at $152. That's good. And then the only one left to close my circuit is here from B to E. So I've got this little star-shaped circuit. Now, remember that Willy has to begin and end his journey at vertex A because that's where he lives. So we can go A, C, E, B, D, A, or we could go in the opposite direction. A, D, B, E, C, A. Either one, they're the same. And if we add up all of these edges, we get 119, 120, 150, 152, 200, for a total of 741. So that is our answer using the cheapest link algorithm. So a couple last things. There are some more algorithms for traveling salesman problems, but we're not going to worry about those right now. This is all we're going to do. Ideally, we would have an algorithm that is both efficient, like our nearest neighbor algorithm, and optimal, like brute force, but to our knowledge, that doesn't exist. So we have brute force, nearest neighbor, repetitive nearest neighbor, and cheapest link as our 4 methods for trying to find a solution to a traveling salesman problem.